So in this video, we're going to look at the separately excited DC machines. And the idea here is to start to shift towards a more practical discussion of electric vehicles, in that we are now going to use the concepts of electric machines to tie into what it is we're trying to do with our electric vehicles. So we'll begin in this video by just introducing or reintroducing, for those of you that are familiar with the DC machine already. We'll discuss the circuit model, we'll discuss its certain parameters, and then in subsequent videos we'll look at how to control the speed, how to control the torque, how to achieve the torque speed characteristics that we look for in our electric vehicles, or our vehicles in general that are based on previous videos. But for now, why don't we just jump right into the circuit model. So the circuit model of a separately excited DC machine looks something like this. So you have an inductance, you have a resistance, you have a voltage source, I guess, or a voltage drop, and you have on this side, you have another winding, we call it, you have a resistance and an inductance. So what's what? You have here, this we call VA, the armature voltage. On this side we have VF, we call this the field voltage. I guess we can also label that this is called the armature circuit, and this is called the field circuit. And these parameters, this is RF, so the field resistance, or field winding resistance. This is the field winding inductance. This is the armature winding, that's not a resistance, that's an inductance. Armature winding inductance, and this is the armature resistance, RA. This thing here we call E, and this is referred to as the electromotive force, and we'll define it in a second. This current here we call IA, so that's the armature current, and then this is IF, and that's the field current. So we say that E, the electromotive force, and that's a strange looking E, so we say that E is equal to K phi omega m. Now this is the speed, so this is the shaft speed, we say. So this is the shaft speed, and this is measured in radians per second. And K phi we call the flux constant. So why don't we say that this thing, K phi is the flux constant, and this is in volt seconds or Newton meters per amp. These are the units that are typically used for K phi. And then we can say that, I mean, we can make another sort of separation, and we say that this is the flux under each pole. This flux is usually measured in Webers, although it could be measured in other units, depending on, I guess, the standard that you're working with. So this is a general setup of the circuit. So I mean, it's a fairly simple circuit when you consider what's going on. But you'll see that there are ways to relate one side of the circuit to the other. For now, let's look at the armature circuit. So in the armature circuit, you have clearly, I mean, if you just write a KVL, you have that VA equals IA RA plus LA DIA by dt plus K phi omega m. And now remember, this thing is E, right? So this here is E, which is the electromotive force. So the input electrical power, I guess, so if we call that P in, is going to equal VA times IA. And so if we write this expression and we simplify it, we'll get three terms. So we have IA squared RA, we'll have plus d by dt, so the time derivative of 1/2 LA IA squared, plus K phi omega m IA. Now, these should look familiar, these terms. So this, we say, is the power lost in RA. Sometimes it's called the ohmic loss. So we'll say the ohmic loss. So we'll say this is power loss in RA, right? And this thing is power exchanged with LA, and this term here is the energy stored in LA. Because remember, this is, you store energy, you don't lose energy in an inductor. You would store it and then you would retrieve it, and the losses are modeled by RA, which would be like the heat of the winding and so on. And this term here must therefore be, we call PM, and we call this the developed mechanical power. Now, this is not a comprehensive overview of how DC machines work. If you're not familiar with that, please review DC machines. This is a summary of what the model is, how we model the circuit, and I guess bare minimum that you need to know to understand these concepts. If you want an in-depth sort of instruction on how these things work, feel free to look at some electric machines references, textbooks and such, perhaps some videos here on YouTube as well. But what we have here is, so we have PM, we define as K phi omega m IA, right? So that is the mechanical torque. But now we know from mechanics that the mechanical torque is equal to, or sorry, the mechanical power is equal to the torque times the angular velocity. And that means that's Tm is the mechanical torque. So this is mechanical torque. So now this can lead us to the following. So we have the mechanical torque times omega is equal to K phi IA, or omega m, I guess, phi omega m IA. Now these are both the same omega, so that's also omega m, I guess. Can be consistent, which then leads us to the fact that the mechanical torque developed in this separately excited DC machine is K phi IA. And this is an important result that we have achieved. So Tm is often referred to as being the electromagnetic or internal torque. The mechanical power and torque available at the shaft are always smaller, though, than the torque power or torque slash power, this here, because there are losses. So this is the internal, but the actual one that we're going to have access to is going to be less than that usually. So in permanent magnet machines, you have K phi, this thing, is a constant, because the magnets are constant, right? So magnets create the fields. K phi, which is the flux constant, is constant, and it does not change. And also the field winding doesn't exist in a permanent magnet DC machine. But we'll look at all those details as we progress. For now, we're just looking at the general case. And finally, the power in a field winding, in the field winding, I should say, does not contribute to any mechanical power, and it's lost entirely in RF. But its purpose is to just establish, I guess the purpose of IF is to establish a magnetic field. Which is why in some cases you can use permanent magnets to bypass that, but those kinds of machines have their own separate issues, right? So now if we look at the field circuit for a second, so let's say field circuit. So if we looked at the armature circuit and we kind of developed some understanding of stuff, but in the field circuit you have VF equals RF. Now this VF is probably going to be troublesome if you think about this relative to the final speed or the steady state speed. We use VF, but this is VF for voltage. And I guess in these discussions going forward, if we discuss that final speed, we'll use capital V for speed and lowercase v for voltage here. So this is IF plus d lambda sub f by dt. Now, this thing is Faraday's law, right? So this is Faraday's law. And lambda f, this is the flux linked by field winding. So whatever flux is linked by the field winding will appear in the field voltage here. And we say usually, so the motor, I mean, I guess you can say that the rotor and the stator, or however you want to consider this thing, but essentially if you have a flux You have let's say a magnet that looks something, or a situation I guess that looks something like this, and you have this thing in the middle like so, and something like this I guess, where this is, and you have a north and a south, and your magnetic field I guess would go this way from north to south. Essentially, you can say that the flux is equal to B times A, where B is the flux density and A is the cross-section area. But again, this is assuming a uniform radial flux density, B, which is a fair assumption to make. We can then say that the flux phi is proportional to lambda F, and the constant of proportionality we call K prime. So phi is equal to K prime lambda F. And again, this is a review of these things, so I'm not spending a great amount of detail in explaining how these things work. So this flux constant is proportional to the flux linked by the field winding and a flux, a constant of proportionality K prime. And we'll discuss, wherever it's relevant, how these things come about. And now the last thing I guess we can discuss for the field winding, since we're discussing circuit models and such, is how the flux and the current are related. So in reality you have, you may recall these curves of magnetic flux versus current, or magnetic field intensity in some cases, and they look something like this, where they kind of saturate out, and they're called like hysteresis curves in some cases. And we're not going to use exactly this curve because they're tedious to work with for the purpose of the things we're doing here, and they're not entirely necessary here. So this is the flux density, and this is H, which is proportional to I, and this is proportional to phi, right? So we can say that since phi and lambda F are proportional, we expect the relationship to fall of lambda F and IF to also follow this curve as well. So you can kind of, by extension, I guess, if you want to say that, you can say that the curve can basically be approximated. Well, there's a couple of things we can say. So the first thing is this. If we operate in this linear region, let's say, so if we make sure that we never exceed, I don't know, something like this region, it's fair to say that this is a fairly linear, you can make a linear approximation of this region. I've exaggerated this, and you can usually ensure that this approximation of a straight line is valid. But in this case, we're going to assume then in our magnetization curve, I guess, the magnetization curve that we're interested in, that this is going to be K phi. So remember, because lambda F and phi are proportional, then IF and K phi should also have the same characteristic. So this is going to be K phi, and I'm going to call this IF. And this curve, again, I'm going to approximate it with a straight line, although it's not a straight line, actually, but for all intents and purposes of the things we're doing for this concept, or these concepts, we can approximate it to be a straight line, and we say that the slope here is equal to KF, is what we call it. So this magnetization is, again, it's approximately modeled by a straight line for the linear region, so I'm assuming that I'm operating within these dashed lines. It's fairly linear. And in the linear region, you have K phi is equal to KF IF. And KF has the units of inductance mentioned. So in steady state, I guess we can summarize everything and have a sort of steady state model. And then based on this steady state model, in the next video, we'll look at speed control. So what do we want to say? We want to say steady state, because steady state conditions are usually what we model our control off of. So in the steady state, we have VA equals IA RA plus K phi omega m. But since these losses are small and the winding resistance is usually low, we say that this is equal to K phi omega m approximately. And you'll notice the inductance term is gone because this is steady state. Now Vf in steady state is equal to If times Rf. And again, you'll notice the lambda term is no longer here because it's steady state. So the Faraday's law term has been dropped because in steady state that term is 0. And then you have the torque is going to be K phi Ia. These three expressions are basically what we'll be using for modeling the, or for controlling, I guess, and modeling the DC machine to operate under the different types of characteristics that we would like to see our machine operate with. So what did we do? We literally just introduced a circuit model, defined some terms, wrote some equations based on these terms. Again, I think the thing to take away from this is, first of all, having this understanding and understanding how these different losses are distributed and how the power is distributed in the different components or the different aspects of the machine. Then you have here, this torque is important, and this is how we'll actually control the torque. Because remember, if you go back to the way that we've dealt with things so far, we've always just assumed that a torque or a force exists. But now we know how we can actually control that. By controlling this armature current, you can actually control the amount of torque you've developed, and then you can make the vehicle go faster or slower by applying different forces. And then we describe the field circuit here, which is, again, based off of this here. And this term actually comes from this multiplied by the current. It's a flux. Faraday's law. I mean, it speaks for itself, I guess. There's not much explanation needed there. And then we discussed this concept of if we have a uniform field, then you can say that this flux constant is equal to K prime lambda f. And again, we're not going into all the details of how all these things work because we're using this for the purposes of modeling. This is not for the physical analysis. If you're interested in the physical analysis, please refer to some electric machines textbook to become more familiar with this stuff. And then we finally concluded that based on these curves, these magnetization curves, if we operate under a small portion of this or a linear portion of this, then we can approximate this whole thing as a straight line, and we can relate K phi to If using Kf, which is the slope of this line. And then, steady state equations, which kind of are just simplified versions of the first equations that we saw. So, I hope this was helpful. If you have any questions, feel free to leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.